A blessed day to each and everyone. Welcome to another professional development for repeated measures analysis of variance. The logical background for a repeated measures or ANOVA, analysis of variance to research situation using repeated measures or related samples, research design. So we are using to analyze variance through measures or some related samples or research designs. Much of the logic and many of the formulas for repeated measures ANOVA are the same to the independent measure analysis that is being introduced. Repeated measures ANOVA includes second stage of analysis, which we're going to study later on, in which variability due to individual differences is subtracted out of the error term. Comparing independent measures and repeated measures ANOVA. The independent measures analysis is used in research situations, for which there is a separate sample of each treatment condition. Then the analysis compares the mean square between treatments. So we have to remember MS stands for mean square to the mean square within the treatments in the form of a ratio. So here we can say that F is equals to mean square between treatments divided by mean square within treatments. What makes the repeated measure analysis is the treatment of variability from individual differences. In this formula, we can say that the treatment effect is 0, which is a null hypothesis which is true. The expected F ratio is 1. So the mean square is between the treatments, and then the mean square is within the treatment. So we can say the treatment effect, we're going to add it with the error, including individual differences, and we're going to divide it, or is it equals divided by the error, including individual differences. There are no individual differences between treatments because the same individuals are tested in every treatment. Variability due to individual differences is not a component of the numerator of the F ratio. So we can see here the F ratio, and individual differences must also be removed from the denominator of the F ratio to maintain ratio with an expected value of 1 when there is no treatment effect. We want the repeated measures F ratio to have the following structure. We can say that F ratio is equal to the treatment effect plus error without individual differences divided by error with individual differences removed. Having said that, we can say that the first accomplished is by two-stage analysis. In the first stage, total variability, or SS, so that's SS stands for total variability, is partitioned into between treatments, total variability, and within treatments of total variability. The components between treatments variability are the treatment effect, if any, and error. Individual differences do not appear here because the same sample of subjects serves in every treatment. Let us all remember, if we are using the same sample, then there will be no individual differences since they are just the same. In the second stage of analysis, we measure the individual differences by computing variability between subjects, or SS between subjects. The value is subtracted from variability between the subjects within, leaving a reminder variability due to experimental error. Here, we can have a total variance, and in the total variance, we are getting it between treatments variant. Number 1, the treatment effect. Number 2, the error or chance excluding individual differences. Wherein here, we're going to have our numerator of F ratio. Within the treatment variance, number 1, these are the individual differences and other errors for number 2. Thus, this is the stage 1. Then, between subjects variance, number 1, individual differences, and the error variance, number 1, error including individual differences. This is the denominator of F ratio. And this is the second stage or stage number 2. Thus, we can say that a similar two-stage process is used to analyze the degrees of freedom. For the repeated measure analysis, the mean square values and F ratio are as follows. So mean square is between treatment is equals to the SS between treatments and the difference between treatments. Wherein we can say that the mean square error will equal to the sample variability of error and the difference of the error. F is equals to MS between treatments and MS over error. One of the main advantages of the repeated measures design is that the role of individual differences can be eliminated from the study. This advantage can be very important in situations where large individual differences would otherwise obscure in the treatment effect in an independent measure studies. Let's see this table. As we can see, this is the step-by-step process of removing treatment effects and individual differences from our repeated measures of data. In letter A, we can say that the original data, including treatment effects and individual differences for the scores SS total is equals to 82. Letter B, the data after the treatment effects had been removed, reducing SS by 50 points. And letter C, the data after the individual differences are also removed, reducing SS by an additional 24 points. So we can see here we have a person A, B, C, D, E. We have the placebo, and there's a drug A, drug B, drug C, person, tools. And we can say we have to identify our mean square and the total ratio. In addition, to determine the significance of the sample mean differences with the hypothesis test, it is also recommended that you determine the size of the mean differences by computing a measure of effect size. This is a common technique for measuring effect for an analysis of variance, that is to compute the percentage of variance that is counted for the treatment effects. In the context of ANOVA, the percentage is identified as n squared. This is ANOVA. This is the Greek letter eta squared. Before computing with the n squared, however, the ANOVA, it is customary to remove any variability that is accounted for by factors other than the treatment effect. In the case of repeated measures design, part of variability is accounted for by individual differences and can be measured by SS between subjects. How are we going to measure effect size for the repeated measures of analysis of variance? When the variability due to individual differences is subtracted out, the value for n squared then determines how much of the remaining unexplained variability is accounted for by the treatment effects. Because the individual differences are removed from the total SS before ETA squared is computed, the resulting value is often called a partial ETA squared. The formula for computation effect size for a repeated measure of ANOVA is equals to n squared equals to SS between treatments, SS total, minus SS between subjects, SS wherein is equals to SS between treatment, divided by 2 SS error plus SS between treatments. So that's just it for today. Thank you so much, and until next time, bye for now, and God bless everyone.